Okay, the next thing I want to look at in section 9.3 is on page 10, the bottom portion, and it's called telescoping sums. Telescoping sums has this particular pattern. You have first term minus the second term, and then the next term has b sub 2 minus b sub 3. And you can see here that the b2 in the first term will cancel out with the b2 in the second term. And it is the name derived from the fact that in simplifying the sum, one term in each parenthetical expression cancels one term in the next parenthetical expression until the entire sum collapses into just two terms, like a folding telescope. So the theorem on this is the sum of a telescoping series is S sub n, the partial sum, is equal to b sub 1, so the first term minus, and then you have the limit of b sub n plus 1 as n approaches infinity. Note, this is not the first term minus the limit of the last term. You must write out the first few terms to decide which terms cancel and which term will stay. Okay, so let's look at some examples on the next page. All right, so in example 6, it says to determine whether the series converges or diverges, and if it converges, you're going to find the sum. So these are examples of telescoping sums. So I'm going to write out that the first term is a sub 1, second term a sub 2, third term a sub 3, fourth term a sub 4, and then I'll just write it out term by term. All right, so for my first one, when it's 1, it'll be 1 over 1, or 1, minus 1 over, and then it's going to be 1 plus 2, which is a 1/3. So there's the first. And then for the second term, when a is equal to, or when n is equal to 2, it'll be a 1/2 here, and then you have a 1/4 here. So it's 1/2 minus 1/4. And then using the same procedure, you have a sub 3 is 1/3 minus 1/5, and then the fourth term is 1/4 minus 1/6. Okay, so notice that you've got all the ones that are canceling out. So if you look at this one here, this one negative 1/3 actually cancels out with something in the third term, 1/3 right here. And then you have a negative 1/4 that's going to cancel out with a 1/4 in this one. So it's not the next term, but it's the next term that it's canceling out with. And if I wrote it out, this will also cancel out, and this will also cancel out, and it'll continue with that particular pattern. And so what happens is all the terms will cancel out except for 1 and a half. So then it converges, it goes to a particular value by the telescoping sum, and the answer is 1 plus a half, which is 3/2. Right, so for this one, this is not a geometric series, so you can't use that formula that we had derived in the previous video. Okay, let's try another one. So for this one here, I have the summation of k is equal to 1 out to infinity of 1 over k plus 1. And I'm going to use partial fractions to rewrite a sub n. Okay, so going back to what we learned before, I'm just writing it out as 1 over, well, this is what I did first. I used the Heaviside method on this. So we have 1 over k times k plus 1, and then I'm writing it as a partial sum, so it's a over k plus b over k plus 1. So using the Heaviside method, I'm going to first of all let k equal 0. So then I cover this one up, and then if I put in 0 for this, I get a is equal to 1. And then when k is equal to negative 1, which is going to make this factor as 0, I cover this up. So cover this part here up. And then I put in negative 1 here. And so I have 1 over negative 1, which is going to give me a negative 1. So b is a negative 1. So I can rewrite this partial sum as 1 over k minus 1 over k plus 1. So that's where I have gotten this. And so I'm going to add up my first few terms. And so simplifying that, I end up with 1 minus a half for my first term. My second term is when k is equal to 2, so that's 1 half minus 1/3. And then my third term is 1/3 minus 1/4. Fourth term is 1/4 plus 1/5. Oh, actually, I made a mistake on here. Sorry. This should be a minus here. Let me fix that. That should be a minus. Okay, so then you can see the ones that are going to cancel out. So the -1 in the first term cancels out with a positive 1/2. -1/2 in the first term cancels with a positive 1/2 in the second. And then the -1/3 here cancels out with a 1/3 and so on. So the only number that remains is my first term answer with a 1. So it converges by telescoping sum, and the sum is equal to 1. Okay, I'd like you to turn off the video and try the next two examples and then come back and check it with my answers. Okay, please pause the video and try the next two. All right, so for C, you had to do another partial fraction decomposition using the Heaviside method. So I rewrote it as 1 over n plus 1 and then times n plus 3. Now notice that sometimes I'm using n's and sometimes I'm using k's. And so you just need to be flexible with whichever variable that you have. All right, so then this becomes a over n plus 2 plus b over n plus 3. So when n is equal to -2, using my Heaviside method, I get a is equal to 1. And then when n is equal to a -3, then b is equal to a -1. Right, so I can rewrite it like this as 1 over n plus 2 minus 1 over n plus 3. And then writing out the first term, the second term, and the third term, I get everything to cancel out except for the first term. So it converges by the telescoping sum, and the sum is 1/3. All right, and the last example on this page, this one you could just write it out. You don't need to do the Heaviside method. So I have first term is 3/4 and then minus 3, and then I get 3/9 minus 3/4 plus 3/16 minus 3/9 plus 3 over 25 minus 3 over 16. All right, so that's my first term, second, third, and fourth. And then I can see the ones that are going to cancel are the 3/4 here and the -3/4. And the 3/9 goes with a -3/9. The 3 over 16 goes with a -3 over 16. So all of these are canceling out, and the only one that remains is the -3. So S is equal to -3, right? So you can see that you have to write out at least the first 4 terms to see which ones are eventually going to cancel out. All right, so that's the telescoping sum. Okay, if you could turn to page 12, and let's go over the final one, which is called the harmonic series. So the harmonic series is one of the most important of all diverging series. So this one actually diverges and arises in connection with the overtones produced by a vibrating musical string. And so the harmonic series is, it's 1 over k, k equaling 0. Actually, this should be a k is equal to 1. So if you could change that to k is equal to 1. Out to infinity. And so you get your first term to be 1, and then the second term is 1/2 plus 1/3 plus 1/4 plus 1/5. So we can see that the sequence converges to 0. Remember, the sequence is different from the series. So even though a sequence converges, it doesn't mean that the series converges, right? But it is not obvious that the series diverges. Although the divergence is slow, by using partial sums, the divergence will become apparent. The sum of the harmonic sequence is a subset of the sum of the values of the function f of x is equal to 1 over x. Okay, so I'm going to show you how it diverges by this next example. Okay, so it says show that the harmonic series it diverges by using the partial sum. So if you look at this right here, you can see that this is a sub 1, right here is 1, and then this is going to be a sub 2, which is a half, a third, a fourth, and so on. Okay, and then this is the partial sums for the harmonic series. And so these are representing the sum. So the first one, the sum is just 1. And then for the second one, if you add up a sub 1 and a sub 2, you get 1.5 and so on. And so the proof on this, I'm going to go back to what we learned in chapter 7. And so here is the proof. Okay, so I have the summation of 1 over k as k is equal to 1 out to infinity. And so I'm going to rewrite this as an integral. So the integral of 1 to infinity of 1 over x dx. I'm just changing the variable there to x's. So now I'm going to use the infinite sum procedure. So you have the limit as b approaches infinity, and then it's lower bound of 1 out to b of 1 over x dx. So I take this integral, which is the natural log of absolute value of x, and then evaluate it from 1 to b, and then take the limit as b approaches infinity. So the natural log of b minus the natural log of 1, and then its limit as b approaches infinity. Natural log of 1 is just going to be 0. And then you have the natural log of, or limit as b approaches infinity of the natural log of b. And so now I'll do this direct substitution. So the natural log of infinity is equal to infinity. It's a very slow procedure of going to infinity, but it still goes to infinity. So here's the natural log graph. It looks like this. So here is at 1. So as it gets larger and larger, as x goes out to infinity, we can also see that y goes to infinity. So here is the limit, which is infinity, so that means that it diverges.